Hi everyone, welcome to our talk. This is Talun Yan, the threat researcher at TS1 Networks, and also accompanied by Shin Li, also is a threat researcher at Trend Micro. Our talk, here's how we will go through our talk. First, we will have an introduction of what is the TEMPEST Attack. Also, we will have an introduction of what is the side channel attack. And then we will talk about what is a USBee, and we will have a little funny demo. First, about what is a TEMPEST attack. TEMPEST is a term dubbed by the National Security Agency of the United States. It roughly looks like this graph. You can actually sniff data through the walls with an antenna. The actual definition of a TEMPEST attack is leaking information through electrical signals, sounds, vibration, or lights, etc. And since electronics products leak electromagnetic waves often, because they have the switch bits from 0 to 1, 1 to 0, that means they're moving electron beams, and thus, inevitably, it will emit electromagnetic waves. You can actually use a little radio to listen to those electromagnetic waves. And this is caused by Faraday's law of induction. Anyway, basically any means of leaking information counts as TEMPEST. A couple of teams around the world had focused on this kind of research since years ago. So in fact, secrets might leak via this way. This is called a side channel attack. In the real world, you can use this attack to your advantage. One is peeping. The most famous example is VAN-ACK phreaking. We will talk about it later. And another use of this is as a side channel. You can use a TEMPEST attack to hop through an air-gapped environment. An air-gapped environment means that this environment is not connected to any other network by any direct means. Think of an isolated lab. The other half of this talk will talk about how to hop through air-gapped environment. Will be presented by Shin. So, VAN-ACK phreaking. Since computer monitors generate electromagnetic emissions, LCD, which is a thinner display we use today, uses a lot of power. And the old big displays, the CRT, actually draws image on the screen by using moving electron beams. Both display cables and processing those image signals leaks emissions since they use large amount of power, and some video adapters also leaks emission. And here's what a VAN-ACK phreaking roughly looks like. On the left hand side you have an ordinary computer screen, which is our victim, and on the right hand side you're an attacker. You can actually sniff the victim screen by using RF emissions, and you can see what the attacker can see on the right hand side. We will then talk about what is a side channel attack. A side channel attack is any attack based on information gained from implementation, such as based on timing, or sound, or electromagnetic, or even power consumption. So, we will have some notable recent examples, like the one we dubbed German tank problem. During the World War II, Allied doesn't have the ability to tell how exact many tanks the Germans have. So, in order to learn how many tanks the Germans have, we will think about German stereotypes. We will think about implementation of German people. They are usually direct rows, organized, and have a rigid structure. Of course, this is a stereotype. But with this assumption, we can assume that being German, serial number on tank parts would be a uniform distribution. Thus, you can deduct how many tanks the Germans have made based on serial numbers from captured or destroyed tanks. Anyway, here's a few categories of side channel attacks. We will talk about timing attacks, power attacks, and electromagnetic attacks. The first one is the most common, a timing attack. You can take a look at his code. This is the code which checks password and gives you a result by returning true or false. We will note that 1. The code is not time constant. You can actually measure time to deduct the length or the correct character of password. Because 1, you can actually know how long the password is, since in the line the arrow has here, the code will have an early return in case of an incorrect password length. Thus, you can measure time from the input to the return to know how long the password is. And also, you can use this to your advantage to guess what the password actually is. So in the indicated line here, you will have an early return in case of correct length but incorrect comparison by character. Since the function uses a for loop, it will return as the program finds out that you have an incorrect character in your password. Another notable example is power. The most famous one is power analysis or differential power analysis. Generally, the power consumption of a CPU is not constant in the runtime. Thus, you can measure power to measure the time taken in certain operations of a cryptography operation. Let's take RSA as an example. RSA decryption is basically ciphertext and raised to the power of private key with a module equals plaintext. The implementation of the power uses square and multiply to calculate. In case of square only, which is a 0, it will take less time, thus less power. In the case of 1, means that you will have a square and multiply, thus takes more power. So you can actually deduct a private key by means of power measurement. And then we'll talk about electromagnetic side channel attacks. You can split them into 2 categories. One is radio, one is by conduction. Radio ones, we have talked about phreaking earlier. And conduction ones, basically any cables used will have a conduction-based electromagnetic side channel, such as power lines, phone lines, or piping, or Ethernet cables. The radio ones, such as magnet phreaking, will roughly look like this graph. So on the left-hand side, the victim will access classified information on his laptop or computer. And the computer system might leak unintended leakage signal, and an attacker can actually retrieve this data by using a high-gain antenna on the right-hand side. And in the case of conduction, on the left-hand side, the user has connected his or her computer system to a physical wire and access classified information via this wire. And on the right-hand side, an attacker can actually use a non-intrusive means to retrieve this data. So basically, your computer system will look like this. Every part of your computer system might actually leak unintended data, such as your display might actually leak RF waves in terms of magnetic phreaking. Your keyboard might actually leak the keystroke you entered. The printer might leak printed information via cable. Your LAN cable might also leak information. So we will start to worry about how we will do our mitigations, since we do not want to have some secret government agencies spying on our data. Well, maybe you can live in one tinfoil tent, as shown as on the right-hand side. But this would be not practical, so maybe you can consider jamming. So, in fact, you can actually generate random noises on all frequencies to prevent eavesdropping via radio. But in fact, this will be both unethical and unpractical, since you have to constantly jamming all frequencies at all times, and also you will run into some legal issues, since you will be jamming off all of the RF frequencies, thus rendering everyone's phone useless. But this is not the end of the world, since you will run into some difficulties of exploiting electromagnetic side channel in the real world. One is that you have to take background noise into consideration, such as consider you're trying to exploit electromagnetic side channel in this crowded office environment. You have a very hard time to tell which signal is which one computer. And also, you need to take background noises from other operations into consideration. As shown here is what you will see during the power analysis of an AES cipher operation. So, if you're running other operations in the background, the measurement might be all messed up, and you will not be able to tell the difference between an actual operation and other operations. And also, you will run into some timing issues, since you don't know what is the start and the end time. So, here concludes the first half of our presentation. We will hand over to Shin.
Hello everybody, my name is Shin, and I'm now going to sharing some topic about the USBee and the USBee. And first, we are talking about USBee. That is a very usual common devices you can find everywhere. And the second is there's a lot of cheap and low quality devices. That means they may not have enough isolation, and this make this good for the research, especially on side channel attack about the emission. So why we choose USB 2 today, not USB 3? The very beginning is that USB 2 is very simple. There's only 4 lines in the cable. There are data plus, data minus, and the voltage and ground. Today we are focused upon the data because for voltage and ground, this kind of power analyzing is very difficult to do, and as previous Darwin shared, that is very hard and very complex to analyze that. So today we are going to talk only about the data. For the data, USB 2 have 3 types. They are low speed, medium speed, and a high speed type. We are focused about high speed type, which provides the bigger frequency range, so it will be easier to catch their side channel attack data. So we are first talking about how the data being transferred in USB 2. The USB 2 uses the non-return to zero inverted type to encoding the data that is good for differential signaling transmitting. That's why there's a simple explanation here. That is, if you transfer the data in a differential type, that is, the data will be transferred both in the positive and the negative phase. When they are received, they will be minus together to convert back to the original signal. So if there's a noise being injected when they are transmitted, the noise will be minus and it will be disappear. So it will be this kind of differential transfer is better when you are transfer high speed data. So for the non-return to zero inverted, the status will be kept to represent 1, and the signal status will be changed when it representing 0. Besides, this picture is taken from the Wikipedia, but this picture isn't inverted, so don't trust the 0 and 1. You have to switch them. For the USB 2 full speed, there will be 480 megabits per second. That means that for the frequency, there will be a maximum 240 megahertz. It will be look like this. This is the main frequency of when a USB is transferring data, and there will be some occurrence frequency around 480. And if you have a better spectrum analyzer, maybe you can find this kind of signal around the 480, but actually they are mainly around the 240. And the signal is usually very dirty. It's just a picture representing how dirty the signal is. So come back to our problem. Why not USB 3? USB 3 is going to achieve 5 gigabit per second. That means the main frequency will be 2.5 gigahertz. That's really fast. We don't have that good antenna and that good devices to catch the signal. And moreover, the USB 3 use the spectrum spread technologies. That means they are use a lot of different frequency around 2.5 to move the most power spike to the 7.5 gigahertz. Of course, we don't have the antenna that is capable for more than 6 gigahertz. And the last one is because the USB 3 is very near to the ISM band. So there's a lot of interference when you are doing research, and you will conflict with the Wi-Fi, Bluetooth, and more transmission. So it's very hard to research. So today we are only focused on the USB 2. Okay, so can we just get everything by an antenna and a RF analyzer? No, because the frequency spectrum is very dirty when you are doing transformation. And you may ask why? Why they're not just pure 240 or 180? That is when you are using a USB interfaces, there are a lot of steps to need to be do before you start transmit. And when you are doing transmit, there are a lot of SETX data. They are not streaming all the time. So for each packet, they have a different sequence and different pattern, and this different pattern will generate different kind of frequency emission. For example, when you are doing synchronized pattern, because synchronized pattern is about 7/0, that is the frequency will change. That means the status will change 7 times when you are doing synchronized pattern, and this will cause about 245 megahertz emission. And then after you are transmitting the packet ID, it will depend on your packet ID. It will be about 60 to 84 megahertz. And there's 3 pictures about the data in, data out, and the start of frame. And they will all generate different they will generate different frequency spectrums based on the data, based on the address, based on the PID, based on their different CRC code. So different data pattern will generate different frequency. And moreover, if they are not symmetric when in their duty cycle, they will make the fixed noise, and this will return to the very dirty frequency spectrum. So there's one maybe we can use, that is the data packet. Because for each data packet, you can extend the data field as long as 1000 bytes. This is long enough to make you observe the data transmission and observe the frequency emission when they transfer the data field. So that's the USB. The USB is an air gap component channel via the electromagnetic emission from the USB, and after our research, we find it's mostly based on this data field. In the paper, we can see this kind of code snap that shows how to emission the specific signal, that is a signal generation code. But will this work? At first, we think, oh, this one is awesome. When we are trying to emission 400 and 402 megahertz, we can see some signals around 400 and 402. But yeah, this looks very good. But what is this? There's there's a 408 signal and it's a power spike, and it is larger than 402, but actually we are trying to imagine the 402. So what happened? We design some research, we design some experiment that I trying to sweep the frequency, and I found this one will just loop and continuous. There's a continuous changing that will be a lot of x, and I found no, this doesn't work. So what's the problem? I'm trying to debug their code in their paper, and I found if I try to generate the 240, yeah, but they will generate a sequence which will emission the 120 megahertz. If I try another data, if I ask him for the 20 megahertz, it just gives some dirty code, and roughly it looks like they will generate about 30 megahertz and 15 megahertz. Will this work? No, this doesn't work. Let's see why. Because 0 will make edges. So actually what it generates is about 96 megahertz, then 240 megahertz and 53 megahertz, and then 240 megahertz. That is very dirty and doesn't represent anything. And is there still something wrong? Yes, that causes bit stuffing. In USB transformation, there will be a bit stuffing mechanism to prevent some unstable type, and which will insert 0 if there's more than 6 continuous 1. Remember that? If the data is 1, the status won't change. If your status won't change for too long time, maybe there was some alias and the data maybe just goes wrong. So let's do coding and trying to fix their code. To emit we choose the 60 megahertz to be our 0. That is a loop of 0111 0111, which will change the status twice in about 408, and okay, it will generate 60 million times when you in a second. And we trying to emit some frequency closer to represent 0, and I trying to send a loop 7 bits. That doesn't work, because this kind of duty cycle doesn't 50-50. That's non-symmetric. They cause a lot of problem. That is a lot of noise. So I trying to emit the 84 megahertz. That is a loop of 10 bits, which is 5 bits. That is change. The status will change twice whenever 10 bits. After that, I think I found that we need a sync mechanism. So I'm trying to think about that. Sync, you can use a spatial pattern. You can use a spatial status. So at the final, I choose a spatial status. So I try maybe I mix to make something noisy. So I try to emit something near 48 to 60 megahertz, and I just combine these 2 bit loops. And yeah, it's really dirty, but it works. So let's see the demo. Hello guys, so this is the demo platform today. There's a notebook which is the main computer and where I run the program, and there's a victim which is a solid status USB disk, and the signal will go from the cable and to the radio equipment, and today I'm using the USRP B210. So let's start it. Okay, I'm now monitoring the spectrum, and I will decode my string into the bit string at about 010101, this kind of string, and 0 and 1 will be the different frequency spike, and there's also a sync mechanism which will between both, and you can find them in the spectrum waterfall diagram. So let's start. Okay, I'm going to send hello blank trend. Okay, the first is edge. You can see there's a sync signal and HEL, L, and O, and blank, and T, and R, then E, and N, and D, and also the new line character. So that's the demo for today. Actually, this demo could be very fast, but I slowed down the demo about 1000 times to make it more easier to be seen. So thanks for your watching and listen today. This is our demo and our topics. Thank you.